Hello everyone and welcome. I am Marco Pegoraro, a PhD student at the Process and Data Science Chair at AWTH Aachen University, and in this talk I'm going to present a use case of process mining analysis on healthcare data and specifically on data from the COVID-19 pandemic. Process mining positions itself at the intersection of process sciences, which are sciences that solve optimizations and operations management and research problems through techniques such as simulation with process data, and data science and techniques more akin to statistics, data mining and machine learning. And process mining bridges these two realities with techniques such process discovery, which learns a model from event data, and conformance checking, which compares models with with historical data to assess the compliance of a process to a normative model. Now, the basis for all process mining techniques is an event log. An event log is a special type of dataset which records events that occur in a process. These events are grouped by case ID, and we can see it in the leftmost column, and every case ID is connected to a specific case that goes through the flows of activities in a certain process. Now, many events are connected with a specific case ID, and these are the activities which are carried out in regard of a specific case. And each event is identified by three key attributes. One is the case ID, so the case to which it is connected. Then there is the timestamp, which is the moment in time a specific event has occurred or it has been registered into an information system. And then there is the activity, which describes the task that has been carried on in that moment in time. So we can see that here at case ID 1, we have a register request, which was the very first event for this process case. And in many cases, other additional attributes can also be available. In this example here, the resource, so the person or agent that carried out that event, or in possibly a cost. The essence of process mining is exactly the grouping of events into traces, and traces refers to the physical sequence of events that is then connected with a case, and that represents the historical events that have been carried out for a certain case. And here we can see the events corresponding to three traces which are connected to three different cases. Now, taking a look at the universe of techniques and algorithms that are available in process mining, we can see that all are centered around an event log, and then there are different classes of techniques that can be applied to event data. So for example, we have discovery here, process discovery, which concerns taking an event log and working out, learning automatically a process model. And process model is a description of how the process works, how the activities are carried out, in which sequence, in which order, and how they interact with each other. Then we have conformance, which is when we take an event log and we do have a process model that describes how the process should be carried out, and measuring the distance, the difference between an event log and a process model, we can verify if the event log, so the data, is compliant with the process model and the process has happened as actually the cases have actually occurred like they are supposed to be occurred, so with no deviations with respect to the expected behavior, or if there are anomalies that occurred in the process. And these are two main examples that are often quoted in regard to process mining, and there are a number of other techniques. So historically, process mining has been developed in the context of business, in the context of management, and in fields like business management and logistics. This historically is the type of data that process mining has been developed for. But process mining is not limited to those domains. And one specific domain of application where process mining is fastly growing in the last years is healthcare. And there are a number of successful use cases and a number of techniques that have been developed recently to analyze healthcare data, healthcare event data with process mining. You can see here, this is an example of a book. This is a collection of use cases of process mining in healthcare. And also worth mentioning is the Pods for Age initiative, which is in a special interest group within the IEEE Task Force of Process Mining, which is specifically dedicated to developing techniques for process-oriented data science, which includes process mining, for healthcare applications. Now, of course, this is something we are all familiar with. The COVID-19 pandemic has hit last year, and this was the main motivation for our work. We know that the COVID-19 pandemic has taken many lives, and together with the loss of human life, the COVID-19 also implied the disruption of every human activity, including all the supply chains and all the production processes in the world, most of them. And this is the main drive behind our work. There is now an ongoing effort, and a huge effort from a lot of communities in every branch of science to analyze the data and the connected phenomenon of the pandemic, to gain insights of what has happened, how it has happened, and most of all, how to mitigate the effect of pandemics such as COVID-19 when they hit. So the main drive behind our research is to apply this science of process mining to data concerning the COVID-19 pandemic. And in this specific case, we are talking about medical data and patients' records. Now, the data that we are specifically going to look at in this preliminary study that we carried out is the COVAS data from the coronavirus Aachen study, which is a collection of data from 216 patients which have been treated at the Aachen Uniclinic Hospital between February 2020 and December 2020. And of those 2016 cases that appear in our event log, 196 cases are complete, so regard patients that have been discharged, and 20 cases were ongoing at the moment that the event log has been exported from the information system. Now, this data contains events which belong to 14 activities, 14 individual activities, which include information on the occurrence of symptoms, the hospitalization and the subsequent discharge of a patient, and in case this patient needs specific treatment, the admission to the intensive care unit of the hospital and the related discharge. Then there are information on the administration of oxygen or on administration of mechanical ventilation for a patient, and also the administration of oxygenation via extracorporeal membrane, the ECMO oxygenation. Now, if we take our event data, we can plot it in a chart which is specific to process mining. This is a data visualization specific to events log. And we can see that here the plot represents every event with a dot. And the dots are sorted by time, and the time is on the x-axis. So we can see the time dimension, which is horizontal in this chart, while in the left-hand side, we can see the cases. So every row of dots represents a case, a patient, and they are sorted by a first event. Now, we can see in the time dimension that it is very, very visible that events related to patients can be clustered in two specific groups, and these two groups represent the so-called two waves of the pandemic, the two waves that have been registered in Germany throughout 2020. And we can see that roughly the two waves are separated by the summer season, where fewer cases have been registered, and specifically fewer critical cases with patients in need of mechanical ventilation. Now, normally dotted charts are color coded, so every dot has a specific color, and we can color code them with any principle possible. We can color the resources, we can color for different clusters of events. In this case, we colored by process cases, so by patient, and we can see in pink patients that have experienced acute respiratory distress symptoms, so RDS, and that then needed mechanical ventilation, versus in green the patients that did not require mechanical ventilations. And this is an example of how we can color code dotted chart in order to have quick insights on a blink of an eye. By just looking at the chart, we can have insights on some specific aspects of the process. In this case, we can observe that the cases that required mechanical ventilations took longer in time to be discharged, while the cases called in green are much shorter, and so the patients have been discharged in a shorter time. Now, in regard to mechanical ventilation, this has been cited by many sources as a critical component of the treatment of a patient for COVID-19. And this is because, of course, of the limited availability of these sort of machines, mechanical ventilators, in ICUs of various hospitals. So it is interesting to see the usage throughout time of mechanical ventilators. And this is possible with the data we have, since for each patient that have been mechanically ventilated is available the moment in time where the mechanical ventilation started, and the moment in time in which the patient has been disconnected from the ventilator. And this plot, which tracks the usage of mechanical ventilators at the same time throughout the year, shows this plot shows the two waves of the pandemic. And we can see that throughout the first wave, the peak of mechanical ventilator used at the same time has been reached. Specifically, it's the 39 ventilators throughout April. And we can see that during the summer there is a minimal usage of ventilators thanks to the fewer critical cases that the city of Aachen and the towns around Aachen have seen of COVID-19 cases, and then the usage of mechanical ventilators goes up again, approaching the winter months. Now, we have talked about the first and second wave of the pandemic, and we can effectively split the data set into two groups of cases. The cases of the first wave, which are 133 cases in the COVAS dataset, and the cases of the second wave, which are 63. So we computed the average case resolution for each of the two clusters of patients. And by case resolution, I mean the average time between the first event recorded for a patient and the last event recorded of a patient. So the difference in time, the distance in time between these two events, averaged across the patients. And if we do that, we can see that the first wave has an average duration for cases of 33 days and 6 hours, while the second wave has an average of 23 days and 1 hour. This is a significant difference. This is a very significant difference in time, and it points to an improvement in efficiency in treating COVID-19 in the Aachen hospital, in the Uniclinic. And these have a set of possible causes. One prominent cause, of course, is the lower ICU occupation. We have seen that the cases in the second wave are 63, while 133 cases belong to the first wave. So this efficiency could spawn from just a lower occupation of the ICU facilities by COVID patients. It is also the case that the medical personnel were just better prepared and better experienced to face the second wave of cases. Of course, this contributes to this increase in efficiency, and also thanks to the investments towards medical equipment and additional resources, also in terms of personnel, there were just better resources and better equipment to face the pandemic in the second phase, and this also made a significant difference in the efficiency with which a patient has been treated. Now, we have touched on process discovery earlier, which is the task within process mining of working out a model of the process from event data. And this is called process discovery. We discover a process model, and this process model is a description of the process expressed in a certain formalism, and many exist actually. Many process models exist of different formalisms, different kinds. We are going now to show a model that is called a Petrinet. Now, these models can also be then automatically discovered, and then anomalies or things that are not reflecting the activities that occur in the process by process experts. So people that have actual experience, first-hand experience of the activities in a process, can correct inaccuracies in this process model to come to a process model that is more reliable. Now here we can see a process model for the COVAS data, and this process model is a description of how patients have been treated in the Uniclinic hospital during the COVID pandemic. And this has been obtained through an algorithm that first discovered it automatically and then allowed process experts to adjust some aspect of the process model to have it better reflect what then happens in reality. So this model is a bit involved. We're not going to go through all the single steps that a patient can undertake within the flow of the process, but we can see that the start of the process would be a patient either showing some symptoms or not showing them. So that is something that might happen or not. The patient can show the symptoms, or that the black transition can skip the activities which represent the start of the symptoms. Then the patient is hospitalized, so he or she is checked in at the hospital, and then separate sets of events can happen in arbitrary orders. So, for example, these symptoms might end at some point during the hospitalization of the patient, and that might happen before or after some treatments that here are administering oxygen to the patient with start oxy and end oxy activities, which are in a sequence. So first, the treatment starts. Every treatment has a start activity, and then that treatment continuously is administered to the patient to the end activity, corresponding end activity. And so we can see that, for example, the ventilation of a patient is a prerequisite for the extracorporeal membranous oxygenation, and then all of this process. So these parallel branches of the process synchronize at the end with an invisible transition in black here that synchronizes the flow of events, and the last two events in the process are in an exclusive or configuration, and the patient is either discharged alive and discharged dead. And this process model has been obtained by a combination of automatic discovery and a slight adjustment afterwards by process experts in a process called interactive discovery. Now, the data available for the COVAS dataset follows this model extremely well. So the data fits the model very well. 98 of the patients, so 98 of the traces can be replayed. So the events in the traces can be executed in that model with perfect fitness. The execution does not comport any anomalies. And this goes for 98% of the traces. So this is an indication of an extremely compliant processes without anomalies, and where the events that have been carried out have also been recorded in an information system with high reliability. So without noise or with very little noise. And these are the conclusions that can be drawn from a very high fitness of the data to a model that is simple, that is humanly readable, as we've seen, and that describes then the process. Now, the conclusions, to conclude this talk, we have seen that process mining techniques are effective in gaining insights from data, also in healthcare settings, and specifically from the COVID-19 pandemic. So this is a preliminary study. So a lot of things have to be done now with data from healthcare and process mining. But these visualizations and this analysis show that gaining insights is possible. So this is a promising approach to analyze healthcare data. And in turn, these insights that are drawn from this process analysis can help fight phenomenon like the COVID-19 pandemic and other pandemics, and giving information on the historic occupancies of mechanical ventilators, on the distribution of cases and the clustering of cases in waves, and so on. Of course, now we need to address a point that is needed to go forward with this sort of analysis. There is an ever-growing need for clean and reliable data, and data without noise. This goes, of course, for all applications of process mining specifically and data science in general, and is a need that is specifically strong in healthcare. More clean data and more reliable data brings in more insights, but to get cleaner and more reliable data, there is a need for automated information recording systems and information systems that can natively support event data like the data we've seen here. This concludes my presentation. I would like to thank you for your attention, and on the screen you can see links for contacting me for further information.